Hello everyone, welcome to this session on algorithmic problem solving. Let us look at the problem of left rotation of an array by d position. So we are given an array of integers and we would like to left rotate it by a given d number of positions. Let us look at the solution.
Our goal is to design an algorithm to cyclically left rotate an array of n elements by d positions. As an example, consider the array 7, 6, 1, 2, 3, 4, 8, 5. Left rotation by d equals 3 positions results in the array 2, 3, 4, 8, 5, 7, 6, 1. This problem arose frequently in implementation of text editors at the Bell Labs, Murray Hill, New Jersey, and was a part of folklore. This is reported by John Bentley in the book Programming Pearls. First, let us consider a simple algorithm. Here we move elements one by one. The leftmost element 7 is moved to the back, and the rest of the elements are pushed left by one position each. Now 6 is in front. Next the element 6 is moved to the end, and 1 ends up in front. Next the element 1 is moved to the end, and 2 ends up in front. The required left rotation has now been completed. Since each move requires n-1 remaining elements to be shifted, it takes order n time. Repeating this d times takes order d n time overall. Space complexity is order n for storing the input array. A question is whether can we improve the time complexity. Now let us consider a second algorithm. Here we first copy the elements to be moved back into a buffer of size d. Then, we move the element 2 in position d equals 3 backwards to position 0. Then, we move the element 3 in position 4 backwards to position 1. Then, we move the element 4 in position 4 backwards to position 2. Then, we move the element 8 in position 6 to position 3. Then, we move the element 5 in position 7 to position 4. Next, we start moving the elements from the buffer back to the end of the array. First, we move 7 from the buffer to position 5 in the array. Next, we move the element 6 from the buffer to the position 6 of the array. Finally, we move the element 1 from the buffer to the end of the array. Now let us compare the two algorithms in terms of their complexity measures. Algorithm A takes order d times n time. We managed to reduce this to order n for algorithm B. Both algorithms use order n storage for storing the input. Algorithm B takes order d additional space for storing the d elements in a buffer. Let us now go to the whiteboard to derive an improved algorithm.
Down the numbers 7, 6, 9, 2, 3, 4, 1, 5. Now, before we get into the algorithm, let us look at one very simple idea from the domain of strings. Okay, this is not a string, but we'll sort of treat it as a string of integers. Now, if I have two strings x, y, then x followed by y denotes the concatenation of the string x with the string y. So x followed by y. And the reversal of this can be written as y reverse, x reverse. So xy whole reverse will be y reverse, x reverse. So if I have something like ABC as your x and your D as your y, and then xy reverse is y reverse, x reverse. So this would be written as A, B, C, D, E whole reverse is y reverse, which is your D, E reverse, followed by A, B, C reverse. And this is nothing but E, D and C, B, A, which is the same as A, B, C, D, E whole reverse. So xy reverse is y reverse, x reverse. And let us make a substitution. Let us replace x by x reverse and y by y reverse. So if you do that, so you get x reverse, y reverse, whole reverse. So I'm just doing a syntactic substitution. So this is y reverse. I'm replacing y with y reverse, x with x reverse. And this would be x reverse reverse. So this would look like a y and x, yx. So in other words, if I have a string xy, to make it transform it into a string y followed by x, we can reverse x, reverse y, and then reverse the entire thing. So we can apply it to our problem in the following way. So we had in our problem, we had this sequence of numbers. So I'm just working with the same example, 7, 6, 9, 2, 3, 4, 1, 5. And we are going to treat this one as our x. So remember that we had to move the entire array cyclically d positions to the left. So this is our, we'll treat this as our x, and 2, 3, 4, 1, 5 as our y. Right? So if you reverse x, then reverse y, and then reverse the whole. So what you will get will be yx. So let's try this out again. Right? So once I reverse this, I get 9, 6, 7. And if I reverse this, I will get 5, 1, 4, 3, 2. And then if you reverse the whole, you will get 2, 3, 4, 1, 5, 7, 6, and 9. And this is exactly what we wanted to do. We wanted to effectively bring the 7, 6, 9 to the back and then push 2, 3, 4, 1, 5 to the left. And we have accomplished that using our idea of reversal. So what did we do? We reversed the first d positions and then reverse the sequence represented by the next n minus d positions, and then again reverse the whole. And we got what we wanted. So implementation of the algorithm will now require 3 reversals, right? So reversals of subsequences. So if we can do the reversal effectively, we will be able to solve the problem that we are trying to solve. Now, how do we do a reversal of a sequence of integers? So you can start, so if you want to reverse this sequence, 2, 3, 4, 1, 5. So you start here and start here, and you start an index I on the leftmost position of the subsequence and an index j initialize with the rightmost position of the subsequence. And then you keep exchanging AI and AJ. And you increment I and decrement j. And you keep repeating this until your I and j meet. And you would have reversed the entire sequence to the what you want. So this would take linear amount of time, linear in the number of elements in the subsequence. So overall, we can say that this process of reversal will take order n time proportional to the number of elements in the sequences. And so that's about it. I think we do 3 reversals, and that accomplishes the cyclic rotation that we wanted to do. What about the space requirement? So in the course of the reversal, we are going to use some temporary variables, and that's a constant amount of extra space. So we have accomplished the following, that we have actually solved the problem in order n time and order 1 extra space. There are 3 algorithms for this cyclic left rotation problem. So the first one we could solve in order dn time, with the space requirement being constant, and then we took a buffer of size d and could bring down the time complexity to order n. And now, keeping the time complexity at order n, we could manage with.
Here is a quick summary of what we achieved. Going from algorithm A to B, we improved the running time from order d times n to order n. But this came at the cost of an extra buffer of size order d. Finally, using algorithm C, we could remove the requirement of the additional buffer while maintaining the running time at order n. Here is the pseudocode and the Python code snippet to implement the reversal used in algorithm C. The function reverse1a implements the reversal as described. The function reverse2 is the alternative Pythonic way of doing the same. Here is the pseudocode and the Python code snippet to implement the rotation used in algorithm C. The function reverse2 can alternately be replaced by reverse1.
Here is a question. How much time does the most efficient solution to the array left rotation problem that we discussed take? Option A. Order n squared time order n space. Option B. Order n log n time and order n space. Option C. Order n time and order 1 space. Option D. Order n time and order 1 additional space besides the space occupied by the input array. Answer. The correct answer is option D. The most efficient solution to the array left rotation problem that we discussed takes order n time and order 1 additional space besides the space occupied by the input array. Here is another question. The array left rotation problem has a user-defined parameter d specified as part of the input. What is the running time of the most efficient algorithm that we presented, if d equals square root of n? Option A. Order n squared time. Option B. Order n times root n time. Option C. Order n log n time. Option D. Order n time. Answer. The correct answer is option D. Order n time. In fact, it is always order n. Here is another question. At most, how many times will each element in the array move in the most efficient array rotation algorithm that we presented? Option A. Once. Option B. Twice. Option C. Thrice. Option D. 4 times. Answer is option B. Twice.
Thank you. This course is brought to you by Elahay Technologies.